Scatterplots are when you are looking at real life data and it follows a particular trend. It doesn't exactly have to be perfect, but for example, if we were to plot some data, and they don't make a perfect straight line, but they fall in a linear pattern, then a scatter plot is just all the points that come together and form a certain trend. So the scatter plot here would be linear. A lot of times if you have two x values that share the same y value, you might get something that's quadratic. So these are all polynomial trends. This is a cubic function. Now exponentials are another type of scatter plot that you're going to be responsible for. And exponentials, what you need to remember about them is they'll grow very rapidly. Your domain for all of these functions, linear, quadratic, cubic, and exponential, are all real numbers. Your range does depend on the function. And the last one, the domain, is all real numbers greater than 0 for the parent function, is the logarithmic curve. And exponentials and logs, as you know from the previous chapter, are inverses of each other. So that's why they look so similar. They're actually just a reflection over the line y equals x. But when you look at data points and they fall in a particular trend, then we're going to create scatter plots. So, and the ones you'll be responsible for in Algebra 2 are linear, quadratic, and cubic, which are some of the polynomial functions, and exponential and logarithmic. So if you look at this set of data here, and we were to plot it, 0, 20, let's use a smiley face, 0, 20, 1 and 13, 2 and 7.5, 3 and 5. We don't have anything for 4 and 5, and that's the other thing about scatter plots is you may not have a value for each one. 6 heads back up to 8. 9, 8 is up here at 20, and 9 is at 29. 9.5 is at 36, and then 10 is up here at 40. Okay, so looking at this, you kind of know it's not linear. Okay, so you might try, no, it doesn't fit a linear model. It doesn't really fit a cubic model. Quadratic, maybe quadratic. Doesn't really fit the exponential or the logarithmic model. So I think for the best bet here is we would go with saying maybe it's a quadratic model because it kind of fits that pattern there. All right, so we're just looking at what type of models they fall into. All right, here's another set of data. Use some flowers here. Much bigger numbers, 1, 20, 205. Oops, let's move that guy over because he's at 1. 2, 2270, so he's going to be very close. 3 is 2350. And this one's a little bit harder since the numbers are so close together. 26 should be right above that line. 5 is at 3, a little above 3000. 6 is a little bit under there. 7 is at 38. 8 is at 45. Now you'll notice the numbers now as we get up here are going to start growing much more rapidly. That's usually an indicator of an exponential, and if you were to go, you would notice it would do something like that. And so if I were to guess what this one is, I would go more exponential on this one. Okay, again, it doesn't really meet the thing of a linear We probably need a little bit more data points to go with it, but I would say of the models, and we'll check these in our calculators, this guy looks pretty exponential to me. So it's going to fit some equation of y equals e to the x. Now you're going to have some other numbers involved with that, but that's what the exponential curve was. And this one's going to be in some format of a quadratic, so it's going to fall into the category of an x squared equation. All right, let's try this one. This one has some negative values associated with it. So -4, -1.6. That's going to be off the chart down here. -3, -2/3. -2, -1/5, which is -1, -1/16, 0, 0, 1/20th. Sorry, I need to move that down. 1/20th is down here. 2, 1/5, 1/5 is 0.2. 3 is 3/4, and 4 is 2, which is going to be off the charts here. So, you know, for this guy, is it linear? No, it doesn't look linear. It doesn't look exponential because we have this drop off. Exponentials level off. So if I were to guess on this one, I would probably guess more of a cubic root. I can't draw very well. And so I would expect to see something along the lines of y equals x cubed for that one. But if you would just go back to the original, all you got to do is plot each of the points x and y and kind of match the pattern of these parent functions. So this is y equals x squared is quadratic, y equals x cubed is cubic, y equals e to the x is exponential, and y equals the ln, which is a natural log, or you might have log of x, or your logarithmic functions. So you're going to match the trend of the points to the parent functions that we're working with here.